Okay, so I repeat. If there is acceleration, if your velocity is changing in one direction, then there is always a force in the direction of acceleration. The force is always in the direction of acceleration. Now, it is quite, most of the time it is said that the friction always opposes motion. But you have to be careful about which motion you are talking about. In the case of this walking problem, the friction is the force that causes me to move. It helps the motion. By preventing the motion of my feet, friction prevents my feet to move, but since I am pushing my feet backwards, and my feet cannot move, my feet are pushing me in the forward direction. So that is why I can move forward, because of the friction between my feet and the surface of the earth. And this direction is always in the direction of friction is always in the direction of the change in the velocity, always in the direction of acceleration. Okay, let's start with some simple examples. We had already solved this problem of a mass on an inclined plane. But this time we are just adding the friction force. And we will assume that initially the object is at rest on the inclined surface. So what will be its subsequent motion? That's the question. Always you first draw the free body diagrams. This is the free body diagram of the mass on an inclined plane. So it has the weight, there is the normal force that the plane exerts on my mass, and there is also the friction force. Since we know from our previous exercise that this mass on an inclined plane, if it's initially at rest, it will try to move downwards. We know that the friction force has to be pointing upwards, trying to prevent that motion. So, okay, these are my, okay. I will choose I forgot to draw the coordinate axis. This is my x direction, this is my y direction. So the forces, there are three forces acting on my mass. One is the normal force, which is in the y direction, positive y direction. I don't know that normal force yet. That is one of the unknowns. There is the weight of the object. This cosine alpha is the angle of the incline. So if you just consider this this continuation of this normal force, this is the angle alpha. So mg is the length of this, the magnitude of this weight force. Mg cosine alpha is the magnitude along the y hat direction, along the minus y hat direction. So we have the weight is minus mg cosine alpha. And there is a component in along the minus x direction with the, since it is the side in the opposite direction of this alpha, it is mg sine alpha in the minus x direction. So this is the weight in these coordinate axes that I choose. X-axis is parallel to the plane, y-axis is normal to the plane. Well, the friction force, it's also in the x-hat direction. Since I know that the object is trying to move downwards, I know that the friction force is in the positive x direction. Well, we know, we have written down all the forces, so we can just write the total force acting on my object. We just sum the y components and sum the x components. So the y component, all the normal force and the weight has a component along the y direction. So it is n minus mg cosine alpha in the y direction. In the x direction, there is the friction force and a component of the weight along the x direction. So it is plus the friction force minus mg sine alpha along the x direction. So this is the total force acting on my mass. Since I know the total force, I know that the acceleration of the object is nothing but this total force divided by the mass. But we know that the object, since it's sitting on an inclined plane, it cannot move in the y direction. So the velocity along the y direction is always 0. which just tells me that the acceleration along the y direction is always 0. So the acceleration along the y direction is 0. It just means that the force along the y direction has to be 0, because if there is a force along the y direction, it should accelerate in the y direction. Well, if the force along the y direction is given by this expression over there, this is the component of the force along the y direction. Since it is 0, we know what the normal force is. Normal force has to be given by mg cosine alpha. Well, the acceleration along the x direction, that is something we would like to calculate, is given by then the x component of the force divided by the mass of the object. So this is the acceleration along the x direction. Now, there are various cases now. It can be that the object doesn't accelerate in the x direction. That is, if the friction force is equal to mg sine alpha. In this case, we know that, well, there is no acceleration. The object always stays at rest. Since the object is at rest, the friction force here is static friction force. But we know that the static friction force, which in this case is mg sine alpha, should always be less than or equal to the coefficient of static friction times the normal force. The normal force we had already calculated. It is mg cosine alpha. So the mg sine alpha should be, for this case to be realized, mg sine alpha has to be less than the static friction coefficient mg cosine alpha, or the tangent of the inclination of the plane has to be less than the static friction coefficient. If the incline is too much, then, well, it's our everyday experience. If you have a book, let's take our experiment. If I put it on this incline, it doesn't move. Because in this case, the slope of this plane, if you call it alpha, tangent alpha, it is less than the coefficient of static friction between the book and the inclined plane. So there is no sliding. If I could increase the slope of this plane, at some moment, we all know that it will start to slide if you just increase the slope. And in that case, if the slope if this condition is not satisfied, then it just tells us that the friction force cannot be equal to mg sine alpha. In that case, the object will start to accelerate. That is, the slope is too high. The object starts to slide. The object will accelerate. The acceleration, we had already derived that it is the friction force minus mg sine alpha divided by m. So it is the friction force, since the object is sliding now, it is the kinetic friction coefficient times the normal force minus mg sine alpha over m. And the normal force, we can just pick it up from here. So the masses, they just cancel. So we have minus g sine alpha, 1 minus tangent alpha, the coefficient of kinetic friction divided by tangent alpha. Well, we know that in this case, the block will accelerate downward. So the acceleration, the component of acceleration along the x direction should be minus. So this minus sign is not fine. So I have a minus sign over here. The ax should be a negative number. G is a positive number. Sine alpha is a positive number. This minus is fine. But this also has to be positive. If this is not positive, then there's something wrong in what we are doing. Now, how can this be negative? If tangent alpha is smaller than mu k, then this number over here can be negative. In that case, our result will not make any sense. But we had already assumed that before we studied the case when tangent alpha is less than the static coefficient friction. Now we are studying the case when tangent alpha is larger than the coefficient of static friction, which we know is we know that this is larger than the coefficient of kinetic friction. So 1 minus this number over here is always larger than 0. So the acceleration is, as we expected, it is negative. It should be negative. Negative meaning that it is accelerating in the minus x direction. Well, there are several other cases that we can study. The previous case was the case when tangent alpha was larger than mu s. But tangent alpha can be such that it is smaller than the coefficient of static friction, but larger than the coefficient of kinetic friction. So since tangent alpha is less than the coefficient of static friction, it just means that initially the slope of the inclined plane is not large enough so that if you put the object at rest, it will stay at rest. That was the first case we studied. But still it is larger than the kinetic friction, which just means that if you don't put the object at rest, but if you just give it an initial push so that it starts sliding, the first push, so it starts sliding. After that first push, it will keep on accelerating. And there is the third case when the tangent alpha is less than the static coefficient of friction, and it is also less than the kinetic coefficient of friction. This just means that the slope is so low that it will not accelerate, it will decelerate. It will slow down. That is, since we are assuming that the friction force is in this direction, we are already saying that in these cases, even when I say that the object is moving, I'm assuming that the object is moving downward, because otherwise the friction force will not be in that direction. So in this case, if you give it an initial velocity, a downward initial velocity, the object will slow down and stop. The slope is not enough to sustain the accelerated motion. Now, any questions on this example? Because the examples will start to get more complicated as we go on. Now, if you remember, in the first week, we were talking about analysis. So the analysis basically meant that if you pick up a complicated problem, we are trying to divide it into much simpler, smaller problems. So now we are essentially studying those smaller parts. We started with a mass on a horizontal surface. That is probably the simplest problem that you can imagine. Then we put it on an inclined plane. Now we are making the problem even more complicated by adding a friction force to the problem. And now the next step, we will add another mass. This is also a problem that we had studied. This is a problem we studied without friction before. Now we have something, we know something new. We know that there are friction forces, so we will see the effect of the friction force in this case. The way we want to approach these kind of problems is always the same. You first draw the free body diagrams. Those are the diagrams that show the mass only and the forces acting on each mass separately. So we know that each mass has a weight. There is a normal force acting on this mass m1 because of the surface. The surface acts with a force n on this mass m1. There's a friction force on this mass. In the case of this second mass, it has a weight, and there will also be a tension force. The string will apply a force on the second mass, while the string will also apply a force on the first mass. So those are the forces that we have. One more. M2. Here. Well, it's a pulley the friction of the pulley we will ignore. A massless, frictionless pulley. And there is a massless string. So these are all the forces. Well, I just denote the forces due to the tension in the string by T1 and T2. So these are our free body diagrams. For each mass, we will use the Newton's law to get an equation for the corresponding unknown quantities. Well, of course, first we need to choose a coordinate system, choose certain directions, let's say, and then write all the forces in these directions. Well, there is the x direction, which is along the slide. There is the y direction, which is perpendicular to the slide. Well, in this problem, I'm also inventing a new direction, the x prime direction. It is the direction in which the second mass is moving. Well, if you want, you can always write this x prime direction in terms of the x and y directions. But in this problem, we will not need it. Well, the weight of the first object, W1, this is the angle alpha. So there is a component along the negative y direction, this one, and it is given by the magnitude of this one times cosine alpha minus m1g cosine alpha. This is the force along the y direction. Well, this has a weight, its weight has a component along the x direction also, which is given by minus m1g sine alpha. So this is the weight. Well, the most complicated expression for all those four forces. We have the normal force. Well, it is simply in the y direction. We have the T1. It is in the x direction. Its magnitude is given by T, the tension of the string. The normal force we do not know. The tension force we do not know. The friction force, well, I will just write it in this form. I don't really know whether F friction is a positive number or a negative number. In this diagram, I assume that just to show the friction force, I just assume that F friction is a positive number, so I assume that it's pointing in the positive x direction, but it need not be the case. Remember, the friction force will always be in the direction to oppose the relative motion of the surfaces. Yes? Well, in this diagram, what I'm assuming, well, by showing the friction force in this direction, I'm kind of assuming that the first mass is trying to go downward, so that T1 is not strong enough to overcome the W1 and the normal force.
So, what the direction of this machine say it accelerates? It accelerates from there. What the direction of this?
Of the friction force, you mean?
Acceleration of the body.
I don't know. At this moment, I do not know the acceleration of the body. It will depend on the masses. If the second mass is very heavy, I know that my mass will accelerate in the positive x direction. If mass 1 is very large, then my object will, mass 1 will accelerate in the minus x direction.
By that time, when it accelerates toward x direction,
okay.
What will be the direction of friction?
Well, the direction of friction is independent of the direction of acceleration.
So it will be a non-positive x direction.
Now, the friction force will always be related with the direction of the velocity, not the acceleration. In the case of kinetic friction, at least. If mass 1 is moving in minus x direction, in that case, I know that the friction force will be in the positive x direction. If mass 1 is, let's say, trying to move in the positive x direction or moving in the positive x direction, then the friction force will be in the negative direction. But at this moment, with this much information, I do not really know what the direction of friction force is, because I do not know at the moment in which direction mass 1 is trying to move. Well, you see, up to this moment, when we were talking about the vectors, the reason why we used the vector notation was that we just ignored about the directions. The sign of the components of the vectors took care of the direction of the vectors, because all equations were vector equations, so things were simple. Now with the friction force, we don't have a vectorial expression for the friction force. So we have to choose by hand what the direction of the friction force is. And in order to choose the direction of the friction force by hand, we have to know in which direction the system is trying to move, because the acceleration the friction force will try to prevent that. But to determine the direction of the friction force, we have to do some more work. At this moment, I don't know the direction of friction. It can be pointing in this direction, it can be pointing in the opposite direction. Well, now we have our forces. We have 3 unknowns in the forces. We don't know T, we don't know N, we don't know the friction force at the moment. So we will need at least 3 equations to solve for these 3 unknowns. Okay, writing Newton's law for the second mass is the easier one, because there are only 2 forces acting on it. There is no friction force. So it has its weight in the minus x prime direction, and there is the tension force due to the string. I will just denote its acceleration by a2 along the x prime direction. I already know that the mass will accelerate only in the x prime direction. It will not move sideways. It will move up and down. So if I write the acceleration vector in this form, then the total force acting on my object will be the sum of these two, t minus m2g x prime. And Newton's second law tells me that the total force acting on an object is its mass times its acceleration. Well, I have a vectorial equality, so the components in each direction should be equal. T minus m2g has to be equal to m2a2. Okay, so I had 3 unknowns. Now this a2 is a 4th unknown, but I have one more equation to relate the unknown t with the unknown acceleration of the second mass. Well, the first mass is a bit more complicated because we have 4 forces acting on the first mass. I will again define the acceleration. I know that this first mass will accelerate along the x direction only. It will not jump out of the plane. So its acceleration will be a1 along the x-hat direction. I don't know whether this a1 is positive or negative at this moment. a1 can be positive, a1 can be negative. If a1 is positive, m1 will accelerate in this direction. If it's negative, it will be accelerating in the minus x direction. Well, I know the forces. I can just sum the forces. This is the sum of the forces. Along the x direction, I know that I have the tension, the component of the weight along the minus x direction, and the friction force. Along the y direction, I only have the normal force and the component of its weight along the y direction, along the perpendicular direction to the surface. And again, Newton's second law tells me that this has to be equal to the mass of the object times its acceleration, m1 a1 x hat. Well, again, now I have a vectorial equality. The components in both sides have to be equal. So it gives me 2 equations. The x component is t minus m1g sine alpha plus the friction force on the left-hand side. On the right-hand side, the x component is just m1a1. They have to be equal. And on the left-hand side, the y component is n minus m1g cosine alpha. On the right-hand side, I don't have any y component, so it has to be 0. So these are the 2 additional equations I have for the unknowns n, t, f friction, and a1. So by just applying Newton's second law to each one of these free body diagrams, I ended up having 3 equations. But I have 5 unknowns. T, N, and the friction force was the forces that the unknowns in the forces, A1 and A2, are the unknown accelerations of my masses. I need 2 more equations. One is the relation between the accelerations. Well, since the M1 and M2 are attached by a string, I know that if M1 moves up by 1 meter, then M2 should move down by 1 meter. So their displacement should be equal in magnitude, at least. But if the displacements are equal in magnitude, then their velocities have to be equal in magnitude. But if their velocities are equal in magnitude, then their acceleration should also be equal in magnitude, at least. The component of the acceleration of this one along the x direction has to be equal to the component of the acceleration of this mass in this direction. But if this is moving in the positive x direction, m1, m2 is moving in the negative x direction. So it has to be equal in magnitude, but opposite in sign, because the directions are opposite. So that just tells me that a2, the acceleration of the second mass along this x prime direction, has to be minus the acceleration of the first mass along this direction. Again, this minus sign doesn't mean that a2 is negative. It just tells me that a2 and a1, they move in opposite directions. If this is moving in the positive x direction, this should be moving in the negative x prime direction. If this is moving in the negative x direction, this has to be moving in the positive x prime direction. Now, I have 5 equations. I have 5 unknown. Well, the friction force, at this moment, we don't even know whether the friction force should be a static friction force or a kinetic friction force. We don't really know. But we can, in general, say that it is some the magnitude at this will be some coefficient times the normal force, less than this number or equal to this number. Now, let's come to the friction force. It depends on the initial conditions. If you are told that initially the first mass is moving, m1, then we know that the friction force will point in the opposite direction. If it is at rest, then the friction force will try to prevent it from starting to move. So to determine what the system is actually trying to do, let's first ignore the friction force. That will tell us what the system will be doing in the absence of friction force. That will be what the system will be trying to do in the presence of the friction force. Let's just ignore it. Then we have these two equations. This is the equation along the x prime direction. This is the Newton's equations along this x direction. We have two equations, two unknowns, t and a1. We had, in fact, already solved this problem in the previous weeks. What you do is just, we are interested in the acceleration, not the tension. If we are interested in the acceleration, I can just subtract this equation from this equation. Then I just get this expression for the acceleration. So it is proportional to g. Well, that is kind of what we expect. If g is 0, there will be no reason for acceleration. Well, if the second mass is too heavy, if m2 is very large, then the acceleration will be positive, telling us that this mass 1 will be moving in the positive x direction, which will tell me that the friction force will be in the negative x direction. If m2 is not that heavy, m2 is less than m1 sine alpha, then the acceleration, this acceleration will be negative. It will be accelerating in the minus x direction. And so the friction force will be, of course, assuming the object is initially at rest, the friction force will be pointing in the positive x direction. So this tells me what the system is trying to do in the absence of friction. And it will allow me to determine the direction of the friction force. Okay, this is what we said. So rather than studying each case separately, let's first take the case that the system is initially at rest. So we create this system, we put the masses on their positions, and we just release the system from rest. And we will assume that the second mass is very heavy. It just tells me that the system will try to move, m1 will try to move in the positive x direction, and m2 will try to move in the negative x prime direction, in this direction. Then the friction force, then I can tell you what the direction of the friction force is. It will be pointing in the minus x direction. Now these are the equations that we have. This is the equation, this is the Newton's law applied to the second mass. This is the Newton's law applied to the first mass. Well, this is the balance of the normal force and the component of the weight along the y direction. So we have three equations and three unknowns, Tn and A1. So this we can solve. Now the friction force in this case, okay. So even if we know that the system is trying to move in this direction, the first mass is trying to move in this direction, the second mass is trying to move in the other direction, because we had assumed that the second mass is heavy, still we don't know whether the system is moving or not. Initially it is at rest, we know that it is the static friction force. It can stay at rest, or it can start to accelerate. These two cases will be different, because the friction force in these two cases will be different. Now let us try to see if the system will stay at rest or not. If the system stays at rest, that basically means that the friction is large enough to balance all the other forces acting on mass 1. So the acceleration is 0. If the acceleration is 0, well, these two forces should balance, so the tension on the string have to be equal to m2 times g. And the friction force, well, let's go back one slide. Here you see if the acceleration is 0, then the friction force should be m1g sine alpha minus t. Well, t is just m2g, because this is also 0. Since in this case, I'm trying to see if the system will stay where it is with zero acceleration. And I'm asking the question, what is the friction force necessary for the system to stay at rest? That is what I'm trying to find now. If I can create such a large friction, then I will say that, okay, the system will stay at rest, it will not move. Well, this is the friction force that I need to keep the system at rest. Even if the second mass is heavy, the system is trying to accelerate in this direction. If I have such a friction force, then the system will stay at rest. Well, remember, we had assumed before that m2 is large enough. m2 is larger than m1 sine alpha. It just tells me that the component of friction along the x direction is negative, which is telling me that the friction force is not really pointing in this direction, it is pointing in the opposite direction. So I think things are going consistently. Well, the magnitude of the friction force, we know that the maximum friction force that we can create at rest is given by the coefficient of static friction times the normal force. We already know the normal force. If the friction force, the magnitude of this friction force, is less than the coefficient of static friction times the normal force, then we know that we can create such a friction force with such magnitude, and so the system will stay at rest. It will not accelerate. If you go back to the example of the book, this is the case when there's a force I apply, but the force I apply is less than the maximum static friction force that I can create. So the object stays at rest. So the friction force, the magnitude of the friction force in this case will be equal to the force that I apply. But if the necessary friction force to keep the system at rest is larger than the coefficient of static friction, in that case, I know that the system, even though it started at rest, it will start to move. Because the friction force will not be strong enough to hold the system at rest. Okay, once the system starts moving, initially the system is at rest. In this case, at least, we are assuming that M2 is large enough so that it starts moving. In that case, the friction is the kinetic friction. This is its component along the x direction. This minus sign just tells me that it is pointing in the minus x direction. The normal force is just m1g cosine alpha. You can just plug this into this equation, substitute the first equation. Well, the rest is just algebra, which you can do at home. And you end up having, this is our acceleration in the presence of friction. Okay, whenever you get a result, you should always ask yourself, does it make sense? Well, if you have other results similar to that case, you should also compare it with it. So this is the acceleration. We can say that if this is the result that we obtain in the absence of friction. If there's no friction force, if there's no second mass, if you remember the first question that first example we studied, we didn't have the second mass, we only had this mass. But that corresponds to the case when M2 is 0. If M2 is 0, then the acceleration is given by this expression. If M2 is 0, then we have minus M1 and divided by M1, they just cancel. So I end up having minus G sine alpha. By the way, this is the result that we obtained assuming that initially the mass is moving upward. Because that is the case we should compare, because in this case also, in this result, we also assume that the system is trying to move upward. So if we just set M2 equal to 0 here, we have minus G sine alpha, it is this term. If I set M2 equal to 0 here, I have minus G mu k cosine alpha. So at least I know that this answer, generalize this answer to the case when I have a second mass attached to the first mass. So it does make sense, what we obtain. If you compare the dimensions, this has the dimension of acceleration. G has the dimensions of acceleration. This ratio doesn't have any dimension because it is the kilogram divided by kilogram. So this term over here has the same dimension as A1. If you look at this term, well, this ratio is again dimensionless, kilogram over kilogram. The coefficient of friction, it is a coefficient relating one force to another force. So it cannot have any dimension. Cosine alpha doesn't have any dimension. So again, this term also has the dimension of G, which has the dimension of acceleration. So we know that in a limit, at least, our equation is our result is consistent with another result that we know, and the dimensions match. So it's probably our result is correct. There's still the possibility that we might have made a sign mistake over here or over there, but nevertheless, it seems to be correct. Any questions? Let's wake up a bit before the break. You started sleeping. Just one more warning though. Some of you got zeros in the first quiz, although you had some right answers because you just cheated from your friend. If you are going to cheat, at least cheat from a friend who you know that will have all the answers right. In all these cases, there's just a few ways to get the right answer, but infinitely many ways to get the wrong answer. So if two of you make the same mistake, it means that you are cheating. And it is always easy to remember the mistakes of others.